Hello all, this is Manjusha Bhosale from KK Polytechnic Nashik. Today we will see the concept of virtual memory which comes under memory management of operating system. Basically the virtual memory is implemented via paging and segmentation. So we will first look virtual memory and then we will go for implementation of paging as well as segmentation. The objectives of this video are to understand the concept of virtual memory, then to know the implementation of paging as well as segmentation, and then we will see the difference between segmentation and paging. So first of all, we should know the purpose of virtual memory or benefits of virtual memory. Virtual memory is used to pretend that our main memory is so big that we can put multiple tasks in it and we can execute them. So virtual memory is a storage allocation scheme in which secondary memory can be addressed like it is a part of main memory. So it is a technique that allow us to execute more and more processes that may not be in the main memory, only its part or some of it are in the main memory and remaining may be on the secondary storage. So generally virtual memory is defined as the separation of user logical memory from its physical memory, that is only part of the program need to be in the main memory for execution, and as per the demand the another part will be loaded into the main memory. So logical address space can therefore be much larger than the physical address space, which is the main memory address space, and logical address space here means the virtual memory space. It allows address space to be shared by several processes and it allows for more efficient process creation. That means even if we have so small main memory, we can still load multiple processes and we can execute them by loading into main memory. Now we will see how it is represented, but before that we should know that virtual memory can be implemented via paging and segmentation, and further the extension of paging and segmentation is demand paging and demand segmentation. So all these concepts we will be going through. Now before going to virtual memory, we should know some of the concept like logical address, physical address, logical memory, physical memory, etc., etc. So what is logical address? When any process is executed by the CPU binds some address to the process and that address is called as logical address. So the address generated by the CPU after execution of any process is called as logical address, and collection of all these logical addresses is called as logical memory or logical address space. Whereas the memory address register store the address of physical memory and that address is called as physical address. So whenever any process is loaded into the physical memory, that is our main memory, the address is assigned called as physical address space, and collectively it is called as physical memory or physical address space. Generally there are three types of address binding: compile time, load time and execution time. So compile time and load time address binding generate similar physical as well as logical address, whereas execution time address binding generate different physical address and logical address. So whenever CPU executes any process, it creates a logical address and that differ from physical address. So there is a need of mapping also. So we will see the purpose of this virtual memory as well as how that mapping is implemented. So here we have to focus on this logical memory, which is the meaning of virtual memory. Now this is the representation of virtual memory, where the logical address space is divided into number of pages and physical memory is divided into number of frames. Indirectly the process is divided into number of pages. The size of each page is same, and physical memory means main memory is divided into number of frames where the size of each frame is same. And one thing here we have to also remember that the size of page and size of frame are equal. So both page size and frame size is equal. To map between this physical and virtual memory, there is one memory map which is also called as page table, which includes the page number and frame number. That means we can find out that which page is loaded into which frame, And there is one more thing here. This is called as a backing store, that is used for swapping purpose. Swapping means whenever we want to get out of the main memory any process, we will just swap out it to the backing store, and whenever we want to execute any process from the backing store, then we will swap in that process into the physical memory. And there are some another reasons also why swapping is necessary, that we will see in next video. But this is what the virtual memory representation. Now what is paging, that already I have told you, but in summary we will again revise it. Logical address space of a process can be non-contiguous. It is the most important benefit of this virtual memory or paging. In previous videos we have seen that whenever I want to load any process into the main memory, I need a contiguous space. So if my process size is 4 byte, then I need 4 bytes of space which should be contiguous. But if you go for paging scheme, then there is no necessity of this contiguous space. So your logical address space, of course, it is divided into pages, and physical address space is divided into frames. So you can load n number of pages into n number of frames, even if you have no contiguous space or non-contiguous space. And generally this physical memory as well as logical address space is divided into fixed size blocks called pages and frames, and the size is power of 2 between 512 bytes to 8192 bytes. So here we have to differentiate between the pages and frames. Pages are the part of logical memory and frames are the part of physical memory, and we keep the track of all free frames also, because whenever we want to load any page into the physical memory, at that time first we need to find out the free frame. To run a program of size n pages, we need n free frames, and then only we will load the pages into the physical memory. And to map between these pages and frames, we need one page table also, that is to translate logical to address, logical physical address. And sometimes there is internal fragmentation. So here we can take one example. Suppose in this example, if I have 4 pages and the last page size is somewhat small, and of course it will be less than the frame size. So when you load that last page into the frame, some of the memory space may be wasted. So that is called as a internal fragmentation. So even if you are using paging scheme, there may be internal fragmentation that will be removed in the segmentation part. So this is what one example where logical memory is divided into page 0 to 3, and all the pages are loaded into the physical memory according to the availability of free frames, and the page table is maintained there, where first column indicates the page index and second column indicates the frame number. So 0th page is loaded to the first frame, first page is loaded to the 4th frame, second is loaded to the 3rd frame, and so on. Here according to the availability of free frames, the pages are loaded, so there are random allocation of the frames. It is not always sequential, that we need to remember. Now how that address translation is happened. Whenever CPU generate a logical address, that logical address contain two parts. First is a page number and second is a page offset. And this page number you can use to find out the frame number in the page table, and then using that frame number, that offset will be combined to the or merged to the frame number, and that will create a physical address of the process. So using the page table, we can convert logical address to the physical address. That means page table also maintain the information about the pages and the frames, and whenever logical address is generated, page table is used to convert logical address into physical address. So here page number is page index and page offset is combined with the base address to define the physical memory address. This is called as the address translation architecture and scheme. This is for paging only. For segmentation it is somewhat different. Now when there are loading and unloading of the pages to the frames, according to the free frames, there is one list maintained, which is a free frame list, and whenever any frame become free, the frame number will be added to the free frame list, and whenever any new page you want to load into the main memory, at that time we have to search the free frame list, and then we will find out the free frame, and according to the availability we will load the page into the free frame. That's why we always get the random number of free frame. It is not always sequential. Now the next topic is segmentation. Before that, there is one more thing that I want to tell. After paging, there is a concept of demand paging, and of course, if there is a demand paging, there is a concept of page fault, page table, page replacement algorithm. These all concepts I will cover in second video, so you can learn the things related to the demand paging in the next video. Now in this video, the next concept is segmentation, and the difference between segmentation and paging is the size of all the pages is same, whereas the size of segmentation is depend on the content of the segment. So it is the memory management scheme that support user view of memory. Here we can think about a program, where a program is a collection of various segment, and a segment is a logical unit like main program, main function, procedure, function, method, object, etc, etc. And according to all these segments, the different segments are generated by the logical address. So in paging we were talking about dividing the logical address space into pages, and here logical address space will be divided into segments, where segments are listed here. Logical address space is a collection of segment, and each segment is of variable length. This is the big difference between paging and segmentation, that there is a different size of segment. This is for the user's view of program, which is a collection of all these things like subrouting, stack, symbol table, main program, and any inbuilt function, and it supports user view of memory. And then the physical memory is divided into number of frames according to the size of segments, and then the segments will be loaded into the main memory. So unlike paging, the physical memory is divided into variable size frames. According to the size of segments, the physical memory is divided, and then the segments are loaded into the physical memory. And there is also need of some memory table, which is also called as segment table here, which consists of 3 columns. First is segment number, second is limit, and third is base. Here segment number indicate the index of the segment, limit indicate the size of the segment, and base indicate the starting address of the physical memory of the segment. For example, here segment 0 is having the size 1000 bytes, and as it is loaded in the frame which base address is 1400, so 1400 plus 1000 is 2400. So this square is what the space for this segment 0. Like this third segment, which has a limit 1100 bytes and base 3200, this is what the space given for the segment 3. So this is the representation of segmentation, where logical address is divided into segments, and the segments are loaded into the physical memory, and there is one segment table which is used to map the logical address into physical address. Now how this will be done, that we can see here. As always, I told you that CPU generates the logical address, but in segmentation that logical address consists of segment number and offset. And whenever we think about this segment number, of course from segment number we will get limit and base, but this offset, it should be greater than 0 and less than limit. If it is less than 0, then of course there is error and the trap will goes to the operating system. If it is greater than limit, then it is out of bound, and again trap will goes to the operating system. So this offset should be in between 0 and the limit of the segment. So suppose here my segment number, suppose for this example my segment number is 1, and suppose my offset is 400. So here I will check, of course 400 is less than 0, it is okay, but what is the limit of third is 1100. So as 400 is less than 1100, it is okay and valid or legal, and so we can add it to the base, and then we can find out the particular physical memory address. So this is how in segmentation the address translation is done. Now here logical address consists of two tuple, segment number and offset, that I told you, and segment table maps two dimensional physical address where each table entry has base and limit. Base means it is a starting address and limit means it is the length of the segment. And there are two register, segment table base register, which store the base address of the segment, and segment table length register store the length of the segment. But of course segment number should be legal, that is it should be less than this limit register, and offset D should be between 0 and segment limit, then only you can get the physical address. From this diagram you can find out it. And this is all about segmentation and paging, and in next video we will see the concept of demand paging, page fault and page replacement with its all algorithms. I hope you will understand all this concept. Thank you.